in sunny Austin, Texas. Today's high is 104 degrees. So today I'm going to be talking to you about what it's like cracking at terahashes scale. I'm not going to make this a vendor pitch in any way. I'm going to focus on the technical challenges that we encounter as we support clients who have, hundreds of GPUs in their clusters. When I first kind of started on this, I kind of thought like 100 GPUs was a really big deal. Now we kind of tend to view 100 GPUs as like meh. Like it's good, but it's kind of middle of the road. There's a lot of distributed solutions for Hashcat out there. But as far as I know, Terahash is the only one that aims to operate at warehouse scale. And what I mean by that is more so with the most recent version, but with every version that passes, we aim to embrace the concepts of data center as a computer. And while we currently don't have any clients who have an entire warehouse full of password cracking hardware, that's the point where we're trying to go. And we try to enable the software to be at that level, even if our clients are not quite at that level. So I'm going to go through the history of how I got started in massive distributed cracking. And I'm going to go through the technical challenges that we faced as we continue to evolve our HASHSTACK distributed solution. So I'm going to start the slide deck. All right. So in the beginning, I kind of got into this because I was messing around with distributed computing. I was doing stuff with MPI, some other Mosaic software, ROX clusters, things along those nature. But all that was all CPU based. And then when GPU cracking came about, we started looking for solutions that would enable us to distribute GPU workloads. So I found a piece of software out of Hebrew University called VIRTUALCL. And I did a presentation on a 25 GPU proof of concept cluster that me and Bitweasel put together at Passwords 12 in Oslo. And when I woke up the next morning after giving that presentation, we had gone viral. We were on the front page of Slashdot, Gizmodo, Boing Boing, NBC News, the Register, like we were everywhere. And in hindsight, I really should have used a lot more than 25 GPUs. I mean, we had more GPUs. That's just what we chose to dedicate to this proof of concept. And had I known in advance in any way that the general public would react how they did to this proof of concept, I would have used like 3 times the number of GPUs. So just, some of the headlines that came out the next morning that I woke up to, which was pretty surreal because I didn't really see this as a big deal. So VIRTUALCL was cool at the time because it was the first solution that I knew of that enabled us to sort of transparently distribute OpenCL jobs across the arbitrary cluster. So what VIRTUALCL does is it provides a virtual OpenCL platform, and the target software, in theory, doesn't need to be aware it's communicating with a virtual platform. It just sees it sees VIRTUALCL as any other, OpenCL platform, just like AMD, NVIDIA, Intel, what have you. So the target software just simply links against libopencl, which is provided by VCL, which then communicates to a broker daemon. And then that broker daemon distributes to the agent daemons, and the agent daemons, which are installed on the compute nodes, actually communicate with the real OpenCL library, be it AMD, NVIDIA, whatever. So in theory, all this is transparent to the end application, but in practice, it didn't quite work that way. We had to have a special fork of OCL Hashcat called VCL Hashcat, which had some workarounds for VCL quirks and such. It also required InfiniBand because it was really latency sensitive. It ended up being a very chatty protocol, and it required essentially real-time communication. Bandwidth wasn't so much of an issue. It pretty much consistently pulled, less than 1 gig of bandwidth, but it was really sensitive to latency. Even just a couple milliseconds was a couple milliseconds was acceptable, but if you start getting up into like double digits of latency, you had a noticeable impact on hash rate. And of course, InfiniBand hardware is expensive. It's way more expensive than Ethernet. VCL was also closed source, and it required frequent updates. So this is back in the time, this is 2012 through 2013, where every GPU driver that was released broke some shit. And then we had to go back in and implement workarounds and fixes, whatever the fuck AMD or NVIDIA broke in their driver that day. And VCL was no exception. So with VCL Hashcat, we had to have our own workarounds for VirtualCL. And then the VCL team, or VirtualCL team, had to turn around and implement any workarounds for any new driver releases every time they were released, which is, a pretty substantial job. The problem is VirtualCL was created by grad school students. This was a grad school project, and they created this their senior year. And when they graduated in spring 2013, that was it. The project died. So when the next version of FGLRX was released, I think that was version 13.9 in September of 2013. We go to install a VirtualCL cluster for a client. This is actually a 64 GPU cluster, which we're just starting out. So this was actually a pretty big deal for us. Like 64 GPUs was pretty fucking cool at the time. But we get OS installed, we get the hardware built, all that shit. And then we go to install VirtualCL and FGLRX, and VirtualCL just shits the bed. So I panic and email Hebrew University. I'm like, you guys really need to update VirtualCL for Catalyst and FGLRX 13.9. And they're like, well, we can't. Everyone who is working on this project is gone. And the intellectual property remains with Hebrew University and MOSIX, so they couldn't just have those people work on it outside of that. I offered to take over the project for them because it was kind of essential to what we were doing, and I didn't want to see the project die. I thought it was really neat. But the professor over there who was in charge of the project was not amenable to that idea. He actually had pretty grave concerns when we first started using VirtualCL for password cracking, because he envisioned us turning the world into a giant botnet. And of course, that wasn't really on our agenda, at least not at that time. But yeah, he really didn't like the idea of his VirtualCL shit ending up in our hands. So we were left high and dry without a software solution. And so we desperately needed something. So we conceived the idea of HASHSTACK. Initially, we thought about making our own VirtualCL clone, since Hebrew University was not going to give us the VirtualCL source code. And we're like, well, fuck it. We'll start our own VirtualCL with, hookers and blackjack. But the more we actually sat down and thought about what that entailed, we determined the level of effort for that was just way too high, and the time frame in which we needed it was way too short. We literally had hardware in-house that we're building for clients who now have no software solution because of VirtualCL. So we decided to make a distributed wrapper, and that's when we came up with the idea of HASHSTACK. Like I said, we had to iterate really quickly on this. So we went from a whiteboard session to production in less than 2 months. And this was basically me and Tom Steele locking ourselves in the office and, ordering over $100 worth of Taco Bell and just banging this out as fast and furious as we could. It had a traditional client server agent architecture. And it was Hashcat focused, but it actually had a generic plugin interface. We had plugins for, and this is before there was just one Hashcat, right? So we had Hashcat, OCL Hashcat Plus, OCL Hashcat Lite plugins, and then we had John the Ripper plugin, and then we had just a generic interface to where any cracking tool could be made to work with HASHSTACK as long as it adhered to a standard format that we had defined. And then it also had the ability to run arbitrary commands when idle. This was less for our clients and actually more for me because we were running HASHSTACK in-house as well for our, cracking as a service type stuff. And this is back in a time when GPU mining was still profitable. So when we weren't working on a password cracking job, I wanted this thing to be generating coins in the background. So the arbitrary idle exec command was literally just put in place so that people could like mine Litecoin or Namecoin or whatever when their cluster was idle. So totally different time. But I mean, it actually worked. It did exactly what it's supposed to do, and it was good. It was good. And the whole goddamn thing was implemented in this fancy new language called Node.js. Again, this is early 2013, so like Node.js was the new hotness, and everyone was starting to move that direction with microservices and everything. And that's something. It's not on this slide, but we implemented HASHSTACK version 1 entirely as microservices. And I shit you not, there was like 23 individual packages that comprised HASHSTACK, and almost all of those were microservices. And we went that direction because that's kind of like the programming zeitgeist at the time, right? Like everyone was pushing microservices and pushing asynchronous and NoSQL and all that other horse shit, right? And in the end, it created more headaches than not if we just had a monolithic fucking program. Maintaining like one server binary and one agent binary is way simpler than like, maintaining 23 individual microservices and making sure that they're all synced and communicating properly, and that the versions are correct, across all 23 packages. And there's just a lot of unnecessary headache that was introduced with that we attempted to manage, but even then, like our clients would still kind of mess it up. Like they would upgrade like 10 of 20 packages, and then like the other ones would just be stuck at old versions, or one daemon would die and another daemon wouldn't know that it's dead, so then it would shit the bed. And anyway, so yeah, Node.js, microservices, NoSQL, MongoDB, all that shit. Tried to use all like the latest and greatest everything, because at the time that seemed like the best idea. And also HASHSTACK was more than just workload distribution. So a lot of our clients at the time thought that HASHSTACK was just a GUI front end for Hashcat. And we're like, no, it's not just a web UI for Hashcat. It actually does like, multi-user and, workload distribution with like a really complex 4-dimensional queuing mechanism. Like you're trying to explain all this to the client, and they're just like, eyes glazed over and like, so it's a web UI for Hashcat. Like fucking yes. Okay. It's a web UI for Hashcat. But it actually did a hell of a lot more than that. In fact, when you installed HASHSTACK on your box, it basically hijacked it and configured it exactly the way that we needed it to be configured. It would actually provision the entire server from just installing like the initial meta package. So it's a complete stack of packages. They get stack, HASHSTACK, that's where it comes from. So it handled driver installation, driver configuration, driver updates. And again, this is back at a time, and even nowadays still kind of a challenge, but this is back at a time when GPU drivers were a pain in the ass to install, and then once you got them installed, it was a pain in the ass to update. So the fact that we kind of handled this automatically was a pretty big value add. Also handled XOR configuration, even though these are headless servers. This is actually during a time where when you had a headless server, you had to have fucking dummy plugs connected to each of the GPUs. There's probably very few people watching this who actually remember that. But yeah, like if you had a completely headless server, each one of those GPUs had to have a special dummy plug attached to it that would connect the necessary pins to trick it to think that there's actually a monitor attached. And we actually had to run XORG because even though these are headless, without XORG, we didn't have the ability to manually set fan speeds or GPU clock rates or set like power tune profiles or any of that. So even though this is a headless server, we still had to have dummy plugs to think there's a monitor attached, still had to run XORG, and still had to configure XORG properly to enable us to control the fans and control the clocks and all the other shit that we needed to do. And then along those lines, HASHSTACK also did GPU tuning for you and also automatic overclocking. And this was kind of a double-edged sword. So when the R9 290X came out, at first it was like entirely unusable because of the way that AMD aggressively implemented PowerTune firmware. PowerTune, I think it was 2.0 at the time. But the GPUs would throttle so aggressively that it was like way slower than the 7970, and it was just essentially unusable. So then I wrote OD6 config. I guess so. I think PowerTune's fucking NVIDIA. Overdrive. I'm sorry. No, PowerTune is AMD. PowerMiser is NVIDIA. All right, whatever. So OD6 config, enabled us to properly configure the R9 290X, but it was still it was good, but it was still kind of mediocre, right? But at that time, when I measured it, it was only drawing 300 watts, which is important because our server platforms like the Brutalis can only handle GPUs that drop to 300 watts. You draw more than that, you're going to blow a fuse on the PCI slots on the motherboard. So we had a automatic overclock profile for the R9 290X that we pushed out to our clients that made the GPU draw just about 300 watts. And then a little bit later down the road, about a year and a half later, AMD pushed out a new driver update that actually caused the power consumption to go up by a good 50 to 75 watts. And we did not know this. This kind of went undetected by us until we started getting a rash of clients who were seeing dead PCIe slots on their motherboards. And all of them had R9 290X based solutions. And I finally busted out a kilowatt and figured out what the fuck was going on. But we actually had the ability through this all these mechanisms that we had in HASHSTACK at the time to enable the automatic overclocking and configuration and all that, to push out a new underclock profile to all of our clients to try to drop the power consumption down to keep it from blowing PCIe slots on the motherboards. So it's both good and bad. The fact that we're able to automatically overclock GPUs, to help get the most speed out of the GPUs is awesome. But then in that one specific scenario, it was bad because we started blowing PCIe slot fuses. But then it was good that we had this functionality because then we could correct it through software over the air and automatically correct it on all of our client systems at the same time, which saved us a lot of money because we were, spending hundreds of thousands of dollars on new motherboards. So yeah. And then, of course, HASHSTACK also had cluster resource monitoring. So there were some drawbacks. Like I said, the entire goddamn thing was written in Node.js. And while Node.js is asynchronous, it also runs on a single CPU thread. That may have changed at some point, but we're talking 2013, that was 7 years ago. And I haven't even touched Node.js since. But at the time, everything ran in a single CPU thread, which was stupid because our cluster controllers had a minimum of 12 CPU cores, 24 threads. And we're sitting here stuck in one thread on the server daemon. So yeah, any long running methods would just totally block the entire application. And we had massive scalability issues. I think the very first alpha that we released to clients could only support 4 nodes. The second one, we were able to get up to 9 or 10 nodes. Basically, anytime a client ordered a cluster larger than the previous largest cluster we had ever built, we ran into some kind of scalability issue, identified some bottlenecks, and had to work to remove those bottlenecks. Unfortunately, 90% of the time, the bottleneck was the fact that JavaScript was too slow for the task that we were trying to do. So we had to re-implement, those bottleneck methods in a faster language and then just shell out to them. So key space calculation was re-implemented in C. Now, calculating key space for a mask attack is really lightweight. But, when you talk about massive dictionaries or rule files, trying to count the number of lines in a file with JavaScript is painfully slow. So that's largely why that entire portion was re-implemented in C. And we just shelled out to that binary to eliminate that bottleneck. Not eliminate, but dramatically reduce it. Regex, anything regex, we actually had re-implemented it in Perl because Perl is amazing at regex. JavaScript is not very good at regex. The primary thing that we were doing with regex here was validating the hash lists, right? So client uploads a hash list, and some of our clients wouldn't even balk at throwing 200 million hashes at HASHSTACK, right, in one job. But then HASHSTACK has to sit there and receive the massively large hash file and then validate each individual hash and then stuff them in a database. And that was a massive bottleneck. So we ended up re-implementing all that in Perl. to try to get that down. And then the agent, like the entire fucking agent, we ended up just implementing the whole thing in Perl. We just got so fed up with everything there. And the only reason we picked Perl at the time is because that's like the only language that we could iterate fast enough in to rewrite the entire damn thing. But yeah, like I said, we also used MongoDB because NoSQL was like, the rage at the time. And out of all the NoSQL databases we tested, Mongo was the most performant. But, then we had clients do things like throw 200 million hashes at HASHSTACK. And that would cause, some not only just, bottlenecks and, blocking processes, but some like really UI weirdness as well. Like, they would go through the process of creating a job, uploading the hash list, and they would just sit there with like the little spinner for a while until it timed out. And then, so they'd go to create the job again because it timed out, right? And then they'd go back like 10 minutes later and find out that other job had finally completed and was actually active and running. But because they went through the process 4 times trying to get it to start, now they have like 4 of the same process running on the cluster. So we threw Redis in front of Mongo as an in-memory caching layer. And that actually had a significant impact, like positive impact. And it enabled us to ingest hashes a lot faster. But still not a very great solution overall. The web UI client was implemented as a single page application in Angular. It was really clunky. It was really heavy. It was really slow. It constantly caused the browser to freeze if you left it up for more than like 30 minutes. And it just had a ton of bugs. And I think probably the most annoying thing is if you're like a Hashcat power user and you sit down and try to use the HASHSTACK web UI, like it was just cumbersome as fuck. There's no way to move quickly in that UI, and it gets very repetitive and very tedious. So there was a lot of drawbacks to having that Angular web UI. I absolutely hated it, and anyone who was like really experienced with cracking and Hashcat and stuff, they also hated it and begged us not to have that again. And we were just severely limited by what we could do in a browser. For non-hash formats at the time, we were scraping everything server side. So like you would actually upload like a PDF or upload a docx or, whatever. And we would, scrape the file server side to get the necessary bits. Like Office to Hashcat and PDF to Hashcat, shit like that. The problem then became like, what do we do with things like, TrueCrypt volumes or really large 7-zip volumes or RAR files, right? Like, are you really going to upload like 100 gigabyte disk image through the browser and just so we can scrape off like 2 kilobytes? Like, no, that doesn't make any sense. So yeah, the browser was an issue. And then we implemented access controls, but there was nothing fine-grained. We assumed that because everyone operating the HASHSTACK cluster was on the same team, that, they all kind of had equal rights and equal access to the cluster, and therefore all users are admins. We didn't have like, different roles or anything. It was just, if you have an account, then you obviously have a right to be there. So therefore you are an admin. And I think some of our clients didn't have a problem with that because it's like, yeah, like everyone on this team does have equal rights and access and privilege to the cluster. So this is totally fine. Other clients were like, this is absolutely unacceptable. I eventually got to the point where the old version 1 code was completely unmanageable. Even just implementing what should have been like a minor bug fix ended up like requiring major refactoring. It just wasn't, because like we threw it together in less than 2 months, so we didn't think of everything in advance, that would come up, and it got really, really hard to implement new features and, try to work around some of the, some of the bugs in there. So we decided we need an entire ground up rewrite for HASHSTACK version 2. And at some point I got the idea to create a commercial fork of Hashcat with native distributed capabilities. And at the time, I was so fucking stoked on this idea. It seemed like the best idea like in the world to me at the time. So we set out to do just that. Now, this is right before Hashcat went open source. And then we started work on this like literally the minute that Hashcat went open source. So we implement in Golang and C with Postgres database. Now we chose Golang because of high concurrency with Go routines, right? So with Node.js, everything ran on a single CPU thread, and we wanted the opposite of that for version 2, right? We're going to learn the lesson on that. So, we wanted, just lots and lots of Go routines to run everything so that we use like, all 24 threads plus on the box. And Golang actually also allows for pretty rapid development. So we thought it was a pretty good choice. But we still stuck with the traditional client server agent architecture. We have, numerous clients and then one server and then however many agents. Meaning that server is both a bottleneck and a single point of failure. So the first thing we had to do is we had to split Hashcat in two. We took everything that had to do with like actually starting a cracking job and executing an OpenCL kernel on a GPU was placed into the agent and nothing else. Like the agent was just like bare bones, trimmed down Hashcat, launch attack on GPU, and that was it, nothing more. And everything else we placed into the server library. And then for any code that wasn't already in Hashcat, such as like the JSON API and the protobufs for agent server communication, workload distribution, multi-user access control. And this time we actually implemented fine-grained multi-role access control. All that was implemented in Go, and then we just linked against the C libraries. And this effort actually laid the foundation for the Hashcat 4.0 refactor with libhashcat. And then because of how clunky our old web UI was, we actually ditched it entirely for a cross-platform CLI, which made our power users like really happy. But our less experienced users were not very thrilled with that decision. They still wanted, a GUI, which fair enough. So our plan initially was to maintain both Hashcat and HASHSTACK trees in parallel. And then if there was any features that we added to HASHSTACK or any like new kernels that we wrote, we would just, backport those as we chose to HASHCAT. This didn't really work out very well in practice though. So when we released version 2, it was in sync with Hashcat 3.5, but it didn't stay that way for very long. And of course we had to add a cross-platform GUI to the roadmap as well because we had significant feedback from our clients that they really wanted the goddamn GUI and they were not happy that we took away the web UI. It turns out this was the single dumbest motherfucking thing I've ever done in my life. I completely underestimated how much work was involved in creating a commercial fork of Hashcat. Like genuinely, I really don't know how to convey how fucking stupid of an idea this was. We spent like 100% of our time just backporting things from Hashcat into HASHSTACK instead of actually adding new features or writing new kernels. Like literally months of work, just backporting Hashcat commits. And that got really frustrating. It's like, hey, are we working on these tickets? Are we working on these features? No, we're working on backports. I got so sick of hearing working on backports. Like, when are we ever going to be done with backports? And then when Adam refactored Hashcat for 4.0, that also meant that we had to refactor HASHSTACK as well. And we hadn't even finished implementing all the backports at the speed that Adam was, committing things to Hashcat. So this was just like absolutely unmaintainable, right? Like, fuck me. And then there was also this other little minor problem where we picked the wrong HTTP library for the API. And this basically limited the server's capability to about 12 nodes. Now, 12 nodes might seem like a lot. That's 96 GPUs. That's a pretty respectable size cluster. The problem is this particular client had ordered 320 GPUs, 40 nodes. And you can't really deliver a 40 node client to a cluster with a server that can only really handle 12 nodes. So this required not a complete rewrite, but a damn near complete rewrite to unfuck, because we use that HTTP library like extensively throughout the code. And there was no like drop-in replacement. So basically anywhere where we were dealing with HTTP, we had to rip out the old library and then, you know, add in all the stuff for the new library. But they did resolve the issue. It was just really painful at the time to have to mess with that. But the server still continued to be a single point of failure and still proved to be a source of bottlenecks as we, tried to build larger and larger clusters. We kept running into problems with the server being a bottleneck and a single point of failure. And we also had clients coming to us asking us if they could order multiple cluster controllers and cluster them together, you know, either high availability or like load balance them or something. And we didn't have a solution for that, but I started thinking about a solution for that. And again, like 40% of our clients were just completely pissed that we had no GUI. So it got to the point where it's like, let's just rethink like the entire fucking thing and just like go as far away from these mistakes as we could possibly get. Like we never ever want to make any of these mistakes ever again. We've learned a lot of lessons from, you know, what we've done over the last 7 years. So, but we need more than just a complete ground up rewrite. Like we need an entire paradigm shift. Like we need to rethink this entire problem entirely and come up with something that's completely different from what's ever been done. So we need to eliminate the single point of failure at the server. We need to enable like actual infinite horizontal scaling. Because again, we always try to strive for like warehouse as a computer, right? We're looking at warehouse scale computing as like the target that we're trying to hit. There should never be any, limiting factors outside of budget for like how many nodes we can support in HASHSTACK, right? And then of course the other big requirement is we have to actually move at the pace of Hashcat development. We have to, as Adam commits things to Hashcat, we need to have those not instantly available in HASHSTACK, but within a very reasonable time frame. So the very first idea that we came up with was let's not do a traditional client server agent model. And let's not even try to cluster the cluster controllers. Let's just eliminate the cluster controllers entirely and make everything peer-to-peer, where all nodes are equal and there are no dedicated servers. And the biggest requirement to this is that work can be submitted to any node. So let's say you have like, 20 users and you have, 10 boxes. Like there shouldn't be just one node that all of them have to hit. They should be able to hit any node in the cluster and, have the same view from any node. And it also needs to be more user-friendly than ever. And also needs to run on Windows. I'll tell you why in a minute. So set out to like figure out how we're going to implement this, because we have the high level requirements, right? Like we know it needs to be peer-to-peer. We know all the nodes need to be equal, all that shit. But how are we actually going to do this? So pretty obviously we're going to need some sort of distributed state machine, right? And that's just straightforward and self-explanatory. But like we just throw a message queue at it and some pub sub and Bob's your uncle. But what about disagreements? Or, maybe even more than disagreements. What about like an actual, rogue cluster member, or a broken, cluster node that's maybe not necessarily intentionally malicious, but is certainly, has, the appearance of malicious behavior, right? So I started coming up with solutions for this. And I somehow got into my head, like, dude, what if computers could vote? Right? Like, uh, you just make it to where, like, if there's a dispute, then one of the nodes like requests a vote, right? And so they take a vote and majority wins. And if there's a tie, like we have an even number of nodes in the cluster, then like literally fucking flip a coin, randomly, or play rock, paper, scissors. Like, why not? And if a peer doesn't accept the results, like then the rest of the cluster just shuns that peer. And I started thinking about, like, is this actually like a thing? Like, can we actually do this? Am I like completely fucking stoned? It turns out that I really didn't have to put that much more thought into it, because this already exists. Like, what I thought up is actually a thing called the RAFT consensus protocol. Now, it's cool that it already exists, because that means that we don't have to do a whole lot to implement it. But it's also cool because it kind of validated my ideas and theories on how to make this work. And told me that I wasn't just completely fucking insane. And we found several implementations of the RAFT consensus protocol. And the one that we ended up liking the most and settled on is AKKA, which runs on the JVM. It's written in Scala. Now, I hate Java. I have shunned Java for damn near my entire life. I completely condemn Oracle JVM. But there is OpenJDK. We don't have to use Oracle. And we don't have to write in Java. We can use Scala and Kotlin. And since I've started work on this, I actually really like Kotlin. I don't really have too many negative things to say about it. It's actually kind of fun to work with. And then AKKA also has some plugins or modules that help us even further, such as AKKA persistence. What AKKA persistence does is it takes our distributed state machine, and which is normally resident in memory, and persists it to disk. And then AKKA distributed data, of course, would be like what implements the distributed state machine. And then on top of all of that, we built a custom multicast-based protocol to enable cluster nodes to automatically discover each other on the network and then automatically join the cluster. Now, we made this opt-in because obviously that's kind of a security risk if anybody can just join the cluster at will. But for some scenarios, like where all of your nodes are on a dedicated subnet that's properly firewalled off, and you have proper layer 3 and layer 4 access controls, this would be a solution that'd be really handy. So, again, thinking about warehouse scale computing or, data center as a computer, let's say you just have racks and racks and racks of compute nodes. You would just unbox one, literally throw it in the rack and power it on, and it would discover the cluster as soon as it's powered on and join the cluster and start doing work. That's kind of the vision that we have for this. And of course, since it's all peer-to-peer, that enables it to actually be just literally that simple. But of course, the default is you manually specify which peers you want to be part of the swarm. Okay, and then in April this year, we had the unique opportunity to present itself to purchase Loftcrack. Dildog approached me, and then we entered negotiations, and we purchased it early this year, primarily for the GUI, which is written in C++ using Qt as the windowing framework. And while it's not currently cross-platform, that's a really easy platform, or that's a really easy language and library to make cross-platform. Instead of HASHSTACK version 3, we now have Loftcrack version 8. And while Loftcrack 7 uses John the Ripper as a backend, we've ripped all that out, and we're in the process of integrating what was HASHSTACK version 3 as the new backend for Loftcrack 8. And the final thing we're doing with this is we are dropping the terahash hardware requirement. Traditionally, we do not let people purchase HASHSTACK as a standalone product. We say, the only way to get HASHSTACK is to buy a terahash appliance, and it comes pre-installed, and that's the only way to get it. But Loftcrack has always been sold standalone. So we are changing the model now to where keeping with Loftcrack being sold standalone, we're going to be selling, Loftcrack 8 as a standalone product without the terahash hardware requirement. So yeah, that's where we are now with development. That's how the product has evolved over time, and that's some of the challenges that we have faced trying to obtain our goal of true warehouse scale computing. Thank you, and hope you've enjoyed this.